All right, now we're recording. All right, so yeah. Hopefully, and I don't know if you saw the video I posted on YouTube yesterday. The trouble was, apparently I was recording the Minecraft audio way too loud, so that's all you could hear. But anyways, 1, 2, 3, 4, 5, 6. We got to sort these people. And as you can see, we've got T followed by a U, then an M, a G, a D, and then a C. So this is clearly not a sorted collection of things. So we already did bubble sort. We already did insertion sort, I think. I always confuse insertion sort and selection sort, but I guess the point is we'll just see a different sorting algorithm. But the cool thing about bubble sort and the other one we saw yesterday, which I think was insertion sort, was okay, what the heck is going on over here? If we got lucky, it would be linear time for sorting. If we got unlucky, it'd be n squared. And that kind of makes sense, you know, for comparing everything to everything else. But let's have a look at this other one, this selection sort. So here's what we're gonna do. I could do this algorithm like in place where we use the same array or collection, but let's not. I'm gonna have everyone go stand over in this corner, and I'm gonna select. Actually, wait. Okay, yeah, stand in this corner, and here's what I'm gonna do. I'm going to look at each and every one of you and find. Oh God, those fish! Can someone please get rid of the fish? How many fish did you all make? This is quite annoying. Just get rid of the fish. Okay, there. Good job. All right, good job. There's still like a demon, but okay. Here's what I'm going to do. I'm going to look at each and every one of you and find the smallest thing. Okay? And also, remember a part of this too is to keep in mind like how much work is being done in total, and have you ever basically done this sorting algorithm before? Whether on purpose or kind of inadvertently, but you know, it worked, so you did it. So here's what we're gonna do. I'm gonna go through and look at each and every one of you and find the one that has like the lowest, like the most important, like the lowest letter, A being low, you know? So I'm gonna see, okay, T. T is the smallest I've seen so far. Okay, CMAC is the smallest now. What do we got? UW, okay, you're not smaller than CMAC. Mecodic, no, you're not smaller. Devious Potato, you're not smaller. And Gabe Camp, no, you're not smaller. So here's what we got. I now went through, I did my linear search through all the existing things, and I now have the smallest thing. So you're gonna come with me, CMAC, and you're gonna stand here at the start of the bell. So now I know I've got, exactly, good job. Now I know, like I did a linear search over here and I found the smallest thing, and then I put it into this list. And this list must be sorted. There's only one thing in it, and it's the smallest thing. So now what I'm going to do is I'm going to go back here, and I'm going to do the exact same thing again. I'm going to do a linear search and find the smallest thing. So I found like the, elephant 8, M, LM, NOP, QRST. Okay, M, now this is the smallest thing I've seen. U, okay, you're not smaller than M. D, you're smaller than M. G, no, you're not smaller than D. Okay, so Devious Potato, you're the smallest thing in the remaining list, right? So yeah, we're going to bring you over here and put you right next to CMAC. Good. Let's do it again. Let's do our linear search. So T, no. M, no. Wait, no, sorry. T, yes, smallest so far. M, you're smaller. U, no. And G, G, you're the smallest so far. So come with me. And yeah, go there. So good. So all I am doing is just a series of linear searches, finding the smallest thing remaining, and we put it there. So, okay, T and M comes before T, and M comes before that. Okay, so perfect, look at that. Then we go T, U, oh, okay, no. So T, you gotta come with me and get in line. Yeah. And then, oh, okay, it's just you. So, get in line there. Ooh. Hey, man, come on, get over there. Get here. Stand in line. Don't, there you go. So there, look, we have our sorted group now. Perfect. So this is actually a really simple sorting algorithm. All we did was repeatedly do linear searches to find the remaining smallest thing and then add it to the sorted list after the previously found smallest thing. That's it. It's really simple. Now, how much work is being done here? because this is a big question. Actually, before we actually talk about that, how many of you, like, raise your hand so I can hear the boops in the chat if you may have inadvertently done this sorting algorithm before? 1, 2, 3, 4, 5. And how many, any of you in here done this sorting algorithm before? You, 6, they're nodding, 7. So a good number of people. 161, yeah, you totally did it, 161. Yep. So there you go. Here's the funny thing. This is a really terrible sorting algorithm. This is horrible. Because no matter what, because remember with bubble sort and insertion sort, we could get lucky and have a linear time. But no matter what, every time I go over here, I have to do a full linear search to find the smallest thing. So I've got to look at all the people that aren't sorted yet, every single time. And how many times am I going to have to come here? Well, I'm going to have to come here and do a linear search for every individual. So the first time I'm going to have to do, now everyone follow me. And I guess I'll stick with the cobblestone. So let's think about it. If I have, so we have 8 people here, right? So the first time I'm going to come and I'm going to do a linear search on and look at how many people. Well, 1, 2, 3, 4, 5, 6, 7, 8. And then I now know I have the smallest person and I can put them in the sorted list. That means there are 7 people remaining. So the next time I do a linear search, how many people are there? 1, 2, 3, 4, 5, 6, 7. And then the next time there will be 3. 1, 2, 3, 6. 4, 5, 6. Then 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. Because every time I remove someone from the unsorted list and add it to the sorted list. So every time I need to go back to the unsorted list to do a linear search, there's one less person I need to look at. But each one of these cobblestone cubes kind of represents like 1 unit of work. And although this is a triangle is just half the square, right? Like this is a right angle triangle, so it's half a square. So if I had something that was like n squared, which would be a square, but I had a coefficient of 1/2. Well, remember, we don't care about coefficients when we're talking about computational complexity. So I have this square here. So how long is the square? Well, 1, 2, 3, 4, 5, 6, 7, 8 by 1, 2, 3, 4, 5, 6, 7, 8. So I had this like 8 by 8 thing. And remember, n was 8. How many things along the bottom do you think we would have if we had n? Well, we would have n things along the bottom, and the leftmost one would always be n. And, exactly, it's n squared divided by 2. But remember that we don't care about the divide by 2. So yeah, it's going to be like n squared divided by 2, which is interesting. But no matter what, it's always n squared. We can't get lucky and get a linear search because every single time, or pardon me, we can't get lucky and get a linear time sorting algorithm by dumb luck of the order in which I look at things like we did with bubble sort and insertion sort. With this sort, you know, I better make sure I've got the right sort here because if not, I may be mixing these two up real bad. Okay, I think what I did was selection sort right here. I'm doing a quick little Google search here to make sure I'm not crazy. Selection sort. Okay, why can't I find, just show me selection sort. Okay, yes, I was doing it right. Has completed, oh, gotta get the drip on. I don't know what that's relevant to, but okay. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, cool. You replaced the top one with bricks. Cool. So no matter what, it's always n squared. So bubble sort, you know, most of the time it's gonna be like n squared. Insertion sort, it's gonna be n squared. But Selection sort is always n squared. There's no getting lucky in this one. Now, no, that's not going to work. Okay, so now let us go back. Here, help me out. Destroy this thing. All right, now let's go back. Where do we have a nice, good area? Here, let's all float above the pool for a second. Come over here. Top of the tree. Well, I want to make sure. No, not in the pool. But why are there, like, monsters in the pool? Yikes. Okay, how? There. Everyone here. Okay. So, here's what we're going to do. I am now going to do a good sorting algorithm. And we're going to start with something called merge sort. Merge sort is fantastic. But it's a recursive algorithm. And I know our knee-jerk reaction is recursion. Oh, I don't know. That's no good. I don't like recursion. Okay, CMAC, no. Let's stop being bad. I know who you are. So, in order for insertion sort to work, or pardon me, in order for merge sort, in order for you to be okay with merge sort, there are two concepts I need you to agree with me on, okay? The first one is if I have an empty list or a list of size 1, that is a sorted list, right? You got to give me that. And it is. Because I could ask the question, is anything out of order in that list? And the answer is no. So therefore, that list is, by definition, sorted. So a list of size 1 and a list of size 0 is sorted. 2, the other thing you got to give me is we could actually, in linear time, merge 2 lists that are already sorted and have a list, the bigger list, that is sorted. So here's what we're going to do here. I'm going to have half of you line up this way in one line, and then the other half line up this way in this line. Okay? Perfect. Perfect, perfect, perfect. So everyone stay. No. Well, no. Ooh, come back. All right. And yeah, you got to be in sorted order. So D, you go before T, and M, you go before T. So we need to start with 2 sorted lists. C, G, ooh, okay, perfect, perfect. So everyone agrees that we have 2 sorted lists here, right? So here's what we're going to do. We're gonna merge these 2 lists. So here's how we merge 2 things. And while I'm doing this, I need you to think about how much work is being done. Now here we're lucky these lists are both size 3. Okay? But I'm gonna look at devious potato and I'm gonna look at CMAC. Okay? And I'm gonna take the one of these 2 that's smaller. That's CMAC. So CMAC, you come stand over here. No, well, over there, right here. Good. Cool. So now I'm going to look at devious potato and Gabe Camb and take whichever smaller. Well, that's D. D comes before G. So D, you come and you stand right next to CMAC. Then I'm now looking at M and G. Well, G comes before M. So G, you're going to go next to these crazy people. Now I'm comparing M to U. Well, M comes before U. So M, I'm going to have you stand over here in the bigger sorted list. M, come on. Hey. Maybe he DC'd or something. No, no, come here. Come here. Yeah, stand next to Gabe, right over here. There, perfect. Okay, sorted list. I need you guys to calm down. And now I'm going to look at these 2 here, and what do we have? We have T and U. Well, T comes before U, so T, you come over here, you stand there, and then U, now we can take you and put you there. And look, what do we have here? Well, we've got, oh, interesting. We've got a bigger sorted list. So right now, we just merged two sorted lists to get a bigger sorted list with a very simple algorithm. Compare the first two things, whichever one's smaller, take it and put in the new one. Then compare the next first two things, like whatever's left over, but the first two. And so on, and so on, and so on, and so on. And that is actually a linear time algorithm, because at most, how many things am I ever going to compare to each other? Well, at most, I'm only going to compare the n things to the, I'm only going to compare, I only need to look at the total number of things we had there. We had two lists of size 3. So it was like size 3 and size 3. So I looked at a total of 6 things. Not 9, not how many 6, not 36, but it was linear. So we can actually merge two sorted lists in linear time. Because think about it, I only ever had to compare, first it was C to G, right? So that was one comparison. Then I compared, no, first I think it was C and D. That's who I compared, right? Here, actually, everyone go back to your original lists and let's just count the number of comparisons we're actually making. So it's only going with like which one half the thing is smaller or the other end thing. I think what you mean is correct, but maybe it was just worded not great. Ooh, I need you over here. Okay, cool. So let's think. So we have a total of 6 people here. How many comparisons did I make? Well, C and M, or C and D, that was one comparison. Now C, you can go back over there. Now D and G, that's another comparison. So D, you can go back over there. Oh, we got an Enderman hanging out. And then we compared G and M. Okay, so G, you can go over there. That's the third comparison. Then M and U. M, well, you can go over there. That's the 4th. Then T and U. Well, T, you go over there. That's the 5th. And then U, well, you just go over here. You're the last thing. So, I mean, I didn't even really need to compare you to anything. But really, it was like 6 comparisons. I guess it was 5, right? It wasn't, like, I didn't have to compare everything to every other thing. I only ever had to compare one thing to one other thing for however many things there were, like, in the lists. So it's linear. It's not quadratic. This is fantastic. So here's what we're gonna do. I'm just keep checking the time because we had a slow start today. So I want everyone to shuffle yourselves and go stand right by the diving board. In line, unsorted. Just try to make yourself unsorted. Don't do it intentionally, but totally do it intentionally. All right, so here's what we're gonna do. Okay, so we have a total of 6 people. This looks good. All right, so we have a total of 6 people. So here's what I'm gonna do. I'm gonna split you in half. I'm gonna have you 3 stay in the order that you're in, but I'm gonna have you 3 come stand on this side here. Okay, and like come closer to the water. And then I'm gonna have you 3 come stand over here, but closer to the water. Okay. No, ooh, not in the water. So now what am I gonna do? Well, you know what? I'm gonna have, I'm gonna split this one here. Now I realize this is a list of size 3, so there's no easy split, but I'm just gonna split like this. So I'm gonna have Gabe and T Elephant come over here. You can float. Do whatever you want. Actually, you know what? No, go back on the ground, but stay on that side. I like that. It's better. And you can just stay there, actually. And I'm going to split you 2 right here. So C-Mac, you can stay there, but M and D, I want you to come over here. And yeah, just stand over here, but out of order. Come on, come here. So, you know what? Oh, we still have 2 people here. You know what I'm going to do? I'm going to split these 2. So I'm going to have Gabe, you're going to stand here. And you're going to stand like here or something, okay? By this torch. And, oh, I'm going to split you 2. So I'm going to have Devious. I'm going to have you go and stand by this torch. And Mechanic, I'm going to have you come stand like over by this torch here. All right, interesting. So now let's take a second and look at what we just have. Like what did we just do? Well, I have one list here of size 1. I have another list here of size 1. I have another list here of size 1. Another list here of size 1. Another list here of size 1. And another list here as size 1. And what do we know about lists that are size 1? Well, they're all sorted, right? Nothing in any of those individual lists are out of order, okay? So I now have, I started with one list of size n that was unsorted. Now I have n lists of size 1 that are all sorted by definition, because a list of size 1 and an empty list is sorted. But remember what else? With that fancy little merge algorithm, I know I can merge two sorted lists, no matter how big they are, but I can merge two sorted lists into a bigger sorted list in linear time. Okay, so I'm going to start by merging these two lists here. So I've got a G and a T. All right, well, G, you're going to come up here and go like there. And then T, you definitely come after the G, so you go there. That was the very simple merge algorithm. Now, stand like there. No, Gabe, you're fine. I'm getting T to stand. Could you sort everything into two sorted lists and then use merge sort? Well, I think you'll see something interesting. So right now, I have one. Guys, I need you to stay in order because you're ruining the rule. So Gabe, stand like here, and T, there we go. Okay, cool. So this is a sorted list, but it's size 2. That's a sorted list of size 1. But hold on, I have a sorted list, and I have a sorted list. So here's what I'm gonna do. I'm going to look at G and U. Okay, well, G definitely comes first. So G, I'm gonna have you stand like here. Then I've got T and a U. Well, T comes before the U. So T, I'm gonna have you stand here. T, get over here. And then you, well, you're left over, so you definitely absolutely go at the end because you're the biggest one in terms of letters, so you go there. And now look, I have a sorted list of size 3, if uwu would stay in order. Now let's go back over here. Well, we've got a sorted list of size 1, a sorted list of size 1. Oh, D, all right, so I'm gonna take D and put you over here by this torch. You're gonna stand between the torch and the water. And M comes after the D, right? And we're just doing the merge. So M, you come stand next to Devious right here. Look at that. So now we have a sorted list of size 2 and a sorted list of size 1. All we have to do is merge. So let's compare the D and the C. Well, the C comes first. So C, yeah, I mean, you can just stay where you are, I guess. D, you definitely go there because we now only have, I mean, we've dealt with the other sorted list. It's already fully over there. So then you two, you can just come on over here. So now we have another sorted list. So we have 2 sorted lists. And what do we do with sorted lists? Well, we just merge them. And we can merge them in linear time. So let's compare the G and the C. Well, the C comes first. So C, I'm gonna have you stand right here. Come here. Okay, now I'm gonna compare the G and the D. Well, D comes first. So D, you come stand here, right next to C. And now we compare the G to the M. Well, G, you will definitely go next to Devious right here. Now I'm going to compare T to M. So M, I think, comes before T. So M, you can go there. And now, I mean, this other sorted list, there's nothing left. So we can actually just take the remainder because I know that these 2 must go after. So you two, just go back on over here in order. Hey, don't ruin my diving board. Not BOGO. Troublemakers. So look at that. We now have one list of size n in order. So we know we can do merge sort. Well, okay. We just saw merge sort. It's awesome. And we know that we can do merges in linear time. But one merge is done in linear time. How many merges are we going to have? Like, how many times are we going to have to do that merge algorithm? Right? Like, how many times is that going to get called? You know? Because, like, do we have any idea on what? So, you know, all these merges are going to take linear time in total. But how many times am I going to have to do those merges? You know? So I had to do like, okay, the merge to get to the big one. And then I merged the list of size 2 and the list of size 1. The list of size 2 and the list of size 1. And I did a merge there and a merge there. But something that was interesting was I had to do a merge here of size 3 and then a merge here of size 3. For a total of 6, right? So here, when I merged the size 3, I did like 6 people. Here, I had something that was size 2 and size 1 to make one list of size 3. And over here, we had size 2 and size 1 to make a list of size 3. For a total of 3 plus 3, well, that's 6. Then we kept going down, and we split that one list of size 2 into 2 more. We had someone standing here and someone standing over here. And then someone standing here and someone standing there. So I had to merge those two together as well. For a total of 4 only in that case, because we got a little unlucky. If we had 8 people, it would have been a little prettier, but it's okay. So, how many? It looks like I had to do merges on like n things for each like level down we went. Until we ended up with, so we started with one list of size n. But when we got down here, we had like n lists of size 1. So how many layers down that like, how many like splits, how many layers down those splits did we have to go to get to our n lists of size 1? Does anyone have any ideas? What are we thinking? I mean, we've seen this relationship before. No ideas? Come on. Oh, I hear a boop. What do we got here for the boop? Log n. Hey, you're absolutely right. The relationship is log n. So the amount of lists minus 1. No, not quite. See, this is the trouble is with the small, if we had 8, this would be a little better. It would fill out, the tree would fill out a little more. That's why I was hoping to get 8 people here, but we're making do with 6. So the relationship is, well, if we keep dividing by 2, divide by 2, divide by 2, divide by 2, divide by 2, until we end up with n things of size 1, well, that divide by 2, divide by 2, divide by 2, that's that like log base 2 relationship, right? So I have log base 2 like layers, and for each one of those layers, I was doing the merge of a total of like n things. So I had to do this linear time thing log n times. So what's the computational complexity of merge sort? Any ideas? What are we thinking? Come on, someone's got to say something. As soon as someone says something, we can end. As soon as someone gets it right. Log n, since the operations are linear. Well, log n is not completely correct. It's going to be n log n. Because we have to do a linear time thing log n times. Right? So it's n log n, which is a hell of a lot better than n squared. So merge sort, awesome. We've got this amazing logarithmic thing in there that speeds things up a lot. Now, I guess with the class on Friday, I'll go a little bit more in how to, I mean, it was kind of hard to explain the computational analysis in Minecraft. So on Friday, I'll do it like I'll draw it out so you can see it a little bit better, and we'll draw it with like 8 numbers. But we did get a visualization of how merge sort works. And tomorrow, and then Friday, I guess we can talk a little bit about quick sort, which is a fun one to think about. But anyways, that's all for today. Let me just, there. Now none of you can cause trouble. And that's it for today. And yeah. I'll see hopefully most of you on Friday. I've never seen a class that was more enthusiastic about having a their final class, but that's, hey, I'm glad you love computer science as much as I do. Anyways, enjoy the rest of your day. See you later. Try to take it easy.